Molecular orbital theory. The goal of this video is to explain why molecular orbital theory is required and when to use it, and to learn how to draw the diagrams for homonuclear diatomics. We'll also want to be able to visualize the basic shapes of the orbitals so that you can understand why some are called bonding orbitals and some are called antibonding orbitals. Remember that we spoke of two theories of bonding. We've already discussed valence bond theory and will now move on to MO theory. In valence bond theory, we discussed how orbitals of individual atoms overlap to form bonds. However, in MO theory, atomic orbitals will instead combine to form molecular orbitals, which belong to the entire molecule instead of one atom. The electrons making up those molecular orbitals will either add or subtract to the bond order. This is the quantum mechanical treatment of bonding. This means that we are going to be using wave functions to determine the shapes of the orbitals. Just like when we learned about wave functions in the quantum mechanics chapter, we won't be doing any of the high-level math, and will instead be looking at the results. This treatment is much better at predicting experimental results. However, because calculations require computers to find the energy levels, it is also extremely complex. Think of all the complex problems that we worked on for hybridization. With MO diagrams, we will only ever work with two atom molecules in this class, and you will only be responsible for knowing the second homonuclear diatomic without hints being given. That being said, in higher level chemistries, they most certainly do this with polyatomic molecules. Let's talk a bit more in depth about MO theory specifically. Similarly to hybridization, however many orbitals you start with is how many we're going to end up with. However, that's where the similarities end. Instead of combining orbitals within an atom, we will be taking them from both atoms in the molecule and using that to form our new molecular orbitals. Each time that we combine two orbitals, one from each atom, we will get two new orbitals. One will be from constructive interference of the wave functions, and the other will be from destructive interference of the wave functions. These will be the bonding and anti-bonding orbitals, respectively. Now let's work through each of these bullet points in more detail. First, let's remind ourselves about what wave interference is. We can think about waves in water to imagine this. We know if two waves crash into each other, they start to cancel out, and this is destructive interference. However, if they come in contact with each other in just the right phase, they can also add to each other, making a bigger wave. This is called constructive interference. We remember from quantum mechanics that electrons act as both waves and particles. This means that they can have interference patterns. Let's take two waves. I've labeled them wave 1 and wave 2. These could interfere constructively or destructively. In this case, I have wave 1 added to wave 1. In other words, I just have two wave 1s. They're interfering constructively because they are at the same phase. So if I add two of these waves together, I get a larger amplitude. In contrast, I could interfere wave 1 with wave 2. And in that case, the peak of this wave interferes with the trough of this wave, and they completely cancel out. Remember that destructive interference does not need to actually completely cancel out, it just needs to lower the amplitude. So how does this relate to orbitals? Let's look at the simplest case first. Two hydrogen atoms bonded together. The two atomic orbitals will merge to form two molecular orbitals. The lower energy will be formed from constructive interference. You will get a shape that should be reminiscent of the sigma bond that we saw in hybridization, although the theory behind it is formed here is quite different. If you instead let the wave functions interfere destructively, you get an antibonding orbital. You can see the shape of this puts most of the electron density on the outside rather than in between the two nuclei. Think about what holds nuclei together. It's a bond, which is made up of electrons. We want the negatively charged electrons to be in between the two nuclei if we want them to be held together, since the nuclei are both positively charged. So this is why the low energy is called the bonding orbital, because much of the electron density is between the nuclei, and the high energy is called the antibonding orbital because much of the electron density is on the outside of the nuclei, pulling the nuclei apart rather than helping them hold together. We denote these by calling sigma and then putting for the antibonding a star to denote the higher energy antibonding orbital. The subscripts tell us where the orbitals came from to begin with. Each one came from the combining of 1s orbitals. When we're making an MO diagram, it's good to have some guidelines. So here are the guidelines on how to make an MO diagram. You'll first want to count your valence electrons and draw the atomic energy level diagrams just like how we did in previous chapters. Do one for each atom that is involved in the molecule. You'll do these along the sides. In the middle, you'll want to put the appropriate molecular orbital diagram. We'll see the basic structures of these in a moment, and you've already seen what the 1s orbitals look like when they combined. You'll then count your total number of electrons for each atom, and you'll fill in from low energy to high energy, obeying all the same rules that you did when using the atomic energy level diagrams. 2 electrons per orbital, and 1 must be spin up and 1 must be spin down. Let's do some examples so you can see how this works. We've already talked about how the orbitals combine to form MO diagrams for the 1s, so we can do the first 4 elements on the periodic table. Here I have drawn out already the basic structure for the atomic energy level diagram, since we know how to do this for previous chapters. So let's look at these one at a time. We have hydrogen right here. We have our 1s, and we have 1 electron in each orbital, because hydrogen each has 1 electron. We then combine to form our sigma and our sigma star. We put our subscript, our star for our anti-bonding orbital. Also note that these split so that 1 is above the 1s orbital, 1 is below the 1s orbital, about symmetrically. Now we'll fill in our electrons. We have 2, and so we fill in from low energy to high energy. Also note that I have our energy axis labeled here. That's important. Make sure you write that this is energy going up. Now for helium. I have drawn out the atomic energy level diagrams already. And now I've put in this basic structure for helium. And we fill in our 4 electrons. And we have this. We can do the same thing for lithium, where we now have 6 electrons total. And the same thing for beryllium, where we now have 8 electrons total. Here I have shown the 1s orbitals for lithium and beryllium. However, often you'll only see the valence orbitals shown, in this case the 2s, and that's perfectly acceptable for this class, the exam included. You don't have to draw the 1s orbitals if you already have electrons in the higher energy levels. Now let's talk about something called bond order before we go on to more complex Lewis or MO structures. This is very similar to the idea of single and double bonds that we discussed in valence bond theory and while doing Lewis structures. However, MO diagrams allow for a bit more flexibility in how these are written because you can have decimal points. Think back to when we drew Lewis structures. How many electrons did it take to make a bond? If you said 2, then you are correct, which means that each electron is worth half of a bond. Any electron that is placed into a bonding orbital will add to its bond order. Any electron that is placed into an anti-bonding orbital will subtract from its bond order. So therefore, you can get an equation that is bond order is equal to 1/2 of the difference between the bonding electrons and the anti-bonding electrons. A bond order of 1 can roughly be thought of as a single bond, 2 a double bond, etc. But here we can very easily get decimal point bond orders as well. Now, because we are only going to be doing diatomic molecules, you'll have whole numbers and halves, but given more complex structures of polyatomic molecules, it is possible to have several other decimal points bond orders as well. Now let's go back to our previous MO diagrams and determine the bond order for each one. First, we'll find the difference between the number of bonding and anti-bonding electrons, and then divide that by 2. So So for hydrogen, we have 2 bonding electrons, 0 anti-bonding electrons. We divide by 2 to get 1. 2 bonding, 0 anti-bonding gives 1. For helium, we have 2 in our bonding orbital, 2 in our anti-bonding orbital for a bond order of 0. Or in other words, that won't form. For lithium, we have 2, 4 in our bonding, 2 in our anti-bonding to give us a total of 1. And for beryllium, we have 4 in our bonding, 2, 4 in our anti-bonding, giving us a total bond order of 0. Now we need to talk about what happens with the p orbitals. Just like with the s orbitals, you combine 2 atomic orbitals, 1 from each atom, to get 2 molecular orbitals, a bonding and an anti-bonding orbital. However, since there are 3 p orbitals in each atom, we also have different ways that these must overlap to form bonds. They can overlap in an end-on-end manner, forming a sigma bonding and anti-bonding orbital. However, the geometry then insists that the other 2 must overlap side to side. You may recognize this as being similar to the pi bonds that we spoke of in valence bond theory. Again, the theory behind them are quite different, but it may help you to remember why there are 2 sets of pi bonding and anti-bonding orbitals, but only 1 set of sigmas. These 6 orbitals will then form from low energy to high energy. The ordering of them does differ a bit depending on the atoms involved, and we're going to see how to determine this momentarily. Once again, our steps are going to be very similar to our last steps, but with an extra step along the way. So we're still going to count our valence electrons and fill into the atomic orbital diagrams along the sides. We then have to decide on which energy ordering our p electrons are going to, or our p orbitals are going to follow when they turn into molecular orbitals. We're going to explain that on the following slide. You then count your total valence electrons from each atom and fill into the diagram in the center from low energy to high. We'll look at 2 of them now and then walk through all of the second row homonuclear diatomics, which you are responsible for knowing. Here are 2 basic outlines of the MO diagram that you'll see. You can see that the 2s and resulting sigma 2s orbitals are the same as before. Once again, you're welcome to draw the 1s and then 1 sigma and 1 sigma star if you like, but it isn't necessary. For the sigma and pi 2p orbitals, sigma star is always highest, and pi star follows. The decision-making comes with the order of the pi 2p and the sigma 2p. You can see that the N2 puts the pi 2p lower, while the oxygen has the sigma 2p lower. For this class, you will have to memorize the direction for each of the second row homonuclear diatomics, but it should be noted the way these actually come about were through calculations done by the computer, and not just the sort of magical hand waving that we're doing here. So give some thought as to why you think that this would be reversed. The next slide will give you quite a bit of hints on this. Everything else about drawing the diagrams is going to be identical. You draw the atomic energy level diagrams off to the side, as I have shown here, followed by the molecular energy level diagrams in the center. Once you've chosen the correct ordering, all the orbitals will be filled from low to high with only 2 electrons per orbital, and 1 must be spin up and 1 must be spin down. Let's look at the entire second row to see how you can quickly decide which molecular energy level diagram is to be used. I have tried to make this a bit more detailed than most general chemistry books so that you can see why the switch in orbital occurs. You can see how the sigma gets closer and closer and closer to the pi orbitals, and then suddenly it comes down even lower. So it's not that there's a magical switch so much as a slow gradient of the sigma moving downward and eventually being lower than the pi. Note that the switch happens to happen between N2 and O2. So you'll know that O2, F2, and Ne2 all follow this pattern, while boron, carbon, and nitrogen all follow this pattern. You should know how to draw each of these diagrams without help. For anything other than the first and second row homonuclear diatomics, I will have to tell you the ordering of the molecular orbitals. Now let's determine the bond order for each example. We have 4 bonding electrons for B2 and 2 antibonding. 4 bonding and 2 antibonding, giving us a bond order of 1. For carbon, we have 6 bonding orbitals and only 2 antibonding orbitals, so we get a bond order of 2. For nitrogen, we have 2 here, 4, 6, 8 electrons and bonding orbitals, 2 in antibonding orbitals, giving us a bond order of 3. For oxygen, we have 2, 4, 6, 8 electrons in bonding orbitals, and then we have 2 in antibonding orbitals here and 2 in antibonding orbitals here, giving us a total of 4 antibonding electrons for a bond order of 2. For fluorine, we still have the 8 bonding electrons, but now we've added more to our antibonding orbitals, and we have 6 in our antibonding orbitals, giving us a bond order of 1. And for neon, we have 8 bonding electrons and we have 8 antibonding electrons, and so we have a bond order of 0. Or in other words, that will not form an E2 molecule. Here's a quick checklist of things to help prevent silly errors. First, make sure you label all the atomic orbitals. Don't forget that those atomic orbitals off to the side need to be labeled with 1s, 2s, or 2p, whichever it belongs. Make sure you label your molecular orbitals. Don't forget about the little subscripts telling you what orbitals those molecular orbitals came from. Don't forget to add the star to the antibonding orbitals. Now, we haven't talked about this yet, but I wanted to add it to the checklist anyways, and you'll see it in the next video. Did you add or subtract electrons as appropriate if you have an ion? You'll need to make sure that you do that on both the atomic orbitals and the molecular orbitals, and we'll learn how to do that in the next video. Did you use the proper order of orbitals for the MO diagrams? Make sure that you're following the correct ordering for the sigma and the pi orbitals. In summary, we now know that MO theory has higher predictive value, yet we choose to use valence bond theory when possible due to its simplicity. We know how to draw MO diagrams for the first and second row homonuclear diatomics, and you have a vague idea of what those molecular orbitals look like. Before coming to class, I want you to do some thinking on the following questions. How does MO theory differ from valence bond theory? How is it the same? Why are there differences in energy levels between the sigma and the pi orbitals of the homonuclear diatomics? And how would we do this for heteronuclear diatomics? Both of you were a scientist in a lab actually trying to figure this out, and as a student in this class.